worked on a series of books, including one book that's about Bayesian statistics, which is what I'm talking about today, and how I ended up working with PyMC Labs, which is a consulting group that does Bayesian statistics and also maintains the PyMC package for doing Bayesian stats in Python. I have been collaborating on this project with the American Institute for Boys and Men. If you are interested in them, the founder, Richard Reeves, gave a really nice Big Think talk. So watch this video. I think it's really good. This talk is partly about the gender gap in SAT scores, but it's also a methodology talk. I'll be talking about using Bayesian statistics to make inferences about selection bias. Motivated in part by this graph. And this is showing the average SAT scores for male and female test takers over roughly the last 50 years. And on average, male test takers have scored about 30 points higher, and this is on a scale from 200 to 500. So it's a pretty substantial difference. This graph comes from a blog post from the American Enterprise Institute, which is described here as a center-right think tank, and in particular, it came from this article from Mark Perry that says that this gap has persisted for 50 years because high school boys are better at math than girls. There was a response article to this that said, well, no, actually, they're not. What's going on here is selection bias, and in particular that the boys who are the worst at math didn't take the SAT. And there was a response article to the response article that said, actually, boys are better at math. So part of what's going on here is that there's a conservative old man who's telling us that boys are better at math, and there are some younger women who might be more liberal, I don't really know, who are saying, well, no, they're not. So this question elicits a lot of tribal thinking along several axes: political ideology, age, gender. So I want to ask you to think for a minute, what do you want the answer to be and why? Where is that coming from? And I will make my sort of personal confession about this, which is that primarily I want to know the answer. I don't have a lot of loyalty to team old white man. I want to know the answer. I also enjoy statistical challenges. So if I'm really confessing, I just want to show off cool statistics. Professionally, though, I also think this matters. It matters because we make better decisions if what we believe about the world is true. It also matters because this conversation is already happening whether we want it to or not, and I think it's better if it's happening in a way that is neutral and data-driven, rather than just, yes, they are, no, they're not. So policy and discourse, I think, is why this matters. Also, statistically, selection bias is the hardest problem in the world, because by the time you've collected your data, it's too late. You usually cannot quantify selection bias, and you can't correct for it, usually. But sometimes you can, and that's what this talk is about. And I'm going to show you kind of a fun example, and then we'll get back to the SAT example. So the fun example is the Poincaré problem. This is Henri Poincaré, the French mathematician. This is a story about him that is almost certainly not true. But I used it as an example in Think Bayes. Here's how it goes. So Poincaré goes to the baker every day, and he buys a loaf of bread. And by law, it's supposed to be 1,000 grams, which is a very large loaf of bread, but it's a nice round number. And he weighs the loaf of bread every day, and at the end of the year, the mean is 950 grams with a standard deviation of 50 grams. So it's consistently too light. He complains to the bread police. The bread police give the baker a stern warning. And the next year, Poincaré goes back, and every day he weighs the loaf of bread. And at the end of the year, the average is 1,000 grams, exactly what it is supposed to be. But nevertheless, Poincaré goes back to the bread police, and they arrest the baker. Why? And the answer is that the shape of the distribution was not Gaussian. What it looked like was the distribution that you would get if you chose 4 loaves of bread and always gave Poincaré the heavy one. So what they suspected is that the baker would see Poincaré coming and heft a couple of different loaves of bread and always give the heaviest one to Poincaré. And since we're all enjoying generative AI today, notice Poincaré's left hand. So here's my first question for you. Is this a plausible story? Like, can you tell the difference between an honest baker and a cheating baker with a sample size of 365? So we're going to do that by sampling the data generating process. We're going to assume that the baker has not changed his evil ways. So the average is still 950, the standard deviation is still 50, but he's selecting 4 loaves and always giving you the heaviest one. And I'm going to generate a sample with size 365. And then we are going to try to estimate the parameters. So this is a kind of a classic Bayesian game where you generate data and then try to estimate the parameters. If we estimate k, which is the number of loaves, if k is equal to 1, that's an honest baker. They pick a random loaf and they give it to Poincaré. If k is 4, then they're clearly cheating, and we're going to see whether we can tell the difference. If you want to see all the details of the model, they are in this notebook. You can run it on Colab. It's all based on PyMC. So I'm going to show you the estimated parameters that come out of the model, and we will compare them with the actual known values. So this is a parameter recovery test to see if we can infer the actual truth that we know. So here is the estimated mean. This is the posterior distribution of the mean. And the posterior mean of the means is 939. Whereas we know that the actual answer was 950. When we generated the data, it was 950. The statistical model estimates that it's 939. And the posterior distribution comfortably covers the actual value. So this is a successful parameter recovery. And remember that the observed mean was 1,000. So the model is correctly figuring out that the underlying distribution from which those loaves were selected had a lower mean. And in particular, notice the upper bound of that distribution. Around 1,000, the posterior probability is quite low. So this model is saying it is very unlikely that these loaves came from a distribution where the actual mean was 1,000. Similarly, with the standard deviation, the observed standard deviation was 35, but the model is telling you that no, actually the original distribution was wider than that. It might have been 54, and we know that the correct value was 50, so again, this is a successful parameter recovery. And then finally, the estimated value for k says, we think on average that maybe the baker is hefting 5 or 6 loaves. 4 is entirely plausible, and in fact, 4 is the most likely posterior probability. But again, if you look at the lower left-hand corner there, it is almost ruled out that k equals 1. So this is, to me, actually surprisingly strong evidence that the baker is cheating. With only 365 data points, we can make a pretty strong argument that k is not 1. The baker is cheating. So that's an example where just by looking at the data, we can infer what the selection process was. And it comes from the shape of the distribution. So if you remember one thing from this talk, it is that sometimes the selection bias will leave a fingerprint in the distributions that you observe that allows you to infer what that selection process was. That's what we're going to try to do with the SAT data. Now, in general, for this to work, you need a model of the data generating process, and you need a lot of data. Fortunately, we have that. So let's get to the SAT example. If you are not familiar with it, the SAT is a standardized test that is used for college admissions. In the US, about 1/2 of graduating seniors who are planning to go on to college will take the SAT. What that means, though, is that there is a strong self-selection process. By and large, people who do not intend to go to college don't take the SAT. And even of the ones who do want to go to college, some might take a different standardized test or none. So, lots of selection. And the question now is, by observing the distribution of scores, can we infer what that selection bias is? As always, start with data. The College Board, which runs the SAT, publishes data, or at least they used to. If you crawl around their web pages and the Internet Archive, you can find reports like this, which have the distribution of scores for male and female test takers. For the math, I was able to find data for 2011 through 15. For the other parts of the test, less data was available. So I'm going to focus on math, partly because I have the most data, but also because there is some literature that suggests that it is the math that probably drives the selection process harder. Like, if you believe that you will do less well at math, you are more likely to decide not to take the test. The range of scores is from 200 to 800. They are scaled so that the mean is usually about 500 and the standard deviation is usually about 100. And we would expect in a very large sample like this for the distribution to be at least approximately Gaussian. And it sort of is and it sort of isn't. So it kind of has the bell-shaped curve that Gaussian curves do, but it gets clipped at both ends. So there are more people at 200 and 800 than we would expect, because all of the people who would get lower or higher in some sense get rolled up into those two extreme points. The other thing is really strong spiky patterns that we kind of have to explain. So truncation makes total sense. Where are those spiky patterns coming from? They are not random. So that's not like binomial distribution random outcomes, because the sample sizes here are like 900,000. So you don't see wiggles like that because of random sampling, but you do see that they are consistent. Like, within 1 year, male and female test takers will have the same spiky pattern. However, the spiky pattern is different from year to year. So what's going on here? There are only 54 questions on the exam. And the scoring system is kind of funny. If you get something right, you get 1 point. If you leave it blank, you get 0 points. But if you answer and get it wrong, you lose 1/4 point. So there are certain combinations that can happen and some combinations that can't. So if you get them all right, you get a 54. If you leave one blank, you get a 53. If you get them all right, but you get one wrong, you get a 52 3/4. But you can't get 53 1/2. And there are other combinations that will be more or less likely because of how the combinatorics works, and some of the questions are more difficult than others. So from year to year, different combinations will be more or less likely. Some raw scores are impossible, and it depends on all of these factors. But we can take advantage of this. So the spikes, as I said, are the same for different groups of test takers, but they vary from year to year, so we're going to use this information. The location and scale of the distributions tends to be consistent from year to year, but different between groups. So, for example, here are the male test takers for all 5 years where I have data. You can see those random spikes being very different from year to year, but the location and scale of the distribution is about the same. And for female test takers, kind of the same. And if I go back and forth, you can see that the two distributions are consistent from year to year, but different between groups. Okay, so that's the other piece of information that we have to work with. Now, thinking about the Bayesian workflow, we have to figure out how to model all of these features that we've just seen. So first, we're going to need an underlying distribution of efficacy. What I mean by efficacy is basically your ability to answer questions like the ones that are on the SAT. And it's some combination of aptitude, which is some basic ability in this area, and achievement, which you could think of as your entire educational history, and some degree of acumen, like are you familiar with this kind of testing and just good at sitting and answering questions for several hours. So we're going to estimate the underlying distribution of efficacy. This is kind of like in the baking problem, estimating the hidden latent distribution of bread weight. The other thing we need to estimate is the selection effect, and presumably people who are less efficacious, they anticipate that their score will be lower, and their probability of taking the test is some function of that expectation. Don't know exactly what the shape of that curve is, so of course it will be a straight line on a logistic scale, so kind of a straight line probability effect. And then the last thing is, in order to model those spiky perturbations, I'm going to use a Gaussian random walk. So those are the essential features of the model. Here are the parameters that describe it. I'm going to have a mu and a sigma that describe the latent distribution of efficacy. Beta, which is going to be the slope of this line that relates your probability of taking the test as a function of your efficacy. And then for the random Gaussian walk, I need a sigma that describes how noisy it is, how much variability there is between consecutive scores on the exam. That's going to allow me to model these spiky perturbations. This naturally turns out to be the hardest part of the model. From a practical point of view, we have to model these perturbations because otherwise the model doesn't work, but we don't actually care what they are. So this is the definition of a nuisance parameter. We have to deal with it, but we don't actually want to know the answer. And as I said, it turned out to be the biggest nuisance of the whole project. One way that I was able to make it work is to, first of all, make sure that when I generate this Gaussian random walk, that it has a mean of 0, so that there's no conflict between estimating the actual intercept of the model and the mean of this random variation. So I have to lock that to 0. I also need to detrend it so that there's no conflict between estimating the selection effect and estimating the random walk. And this is part of the game of designing these kinds of Bayesian models, which is that you need enough parameters to capture the details of the phenomenon. But if you have so many parameters that they are now fighting with each other, you get into these non-identifiability problems where the model can't actually tell you whether it's this parameter or that parameter, and the model behaves badly and produces unreliable results. So this is probably the hardest part of this project for me, is figuring all of that out. The other small nuisance to work out was how to model the sensor data at the beginning and the end. You can think of this as a data censoring problem, which is that if someone's underlying efficacy was 850, they're going to get an 800. If it's 150, they're going to get a 200. So that turns out to be not that hard to model. The underlying efficacy is on a scale from 100 to 900. So we just stretch the range a little bit, compute that PDF, and then take all of the extra probability from the tails and roll it up into those little bumps that you can see on the left and the right. So that's that feature. So that's it. That's kind of the high-level description of the model. If you want all the details, again, there's a notebook there. It runs on Colab, so click that link, press play all, and you can run the model. I'm going to show you some results first for a single year, single gender, and then we'll generalize it to handle all the data. So I'm going to start with male test takers from 2015. And estimate the mean and standard deviation of this latent distribution of efficacy. Comes out to a mean of 526, standard deviation of 120, and The slope of that function, the selection effect, is kind of small, like 0.048. That doesn't mean very much until we use that to compute this line. So for a given beta, we can compute this function, which is the probability of taking the test, as a function of underlying efficacy. What this says is that if somebody kind of knows that they're going to get a 200, then maybe they only have a 48% or 47-ish % chance. And if they think they're going to get an 800, then they have maybe a 53% chance. Now, the midpoint of this is kind of arbitrary. I just fixed this at 0.5, so I'm not trying to estimate the overall fraction of people who take the test. I'm only trying to estimate how much the slope of this line is. And what this says, looking at just 1 year, is I don't have strong evidence that there is a selection effect happening here. And the width of those confidence regions says my estimate is not very precise, and it could, in fact, be practically 0. Next thing I want to do to make sure that this model makes sense is a posterior check where I use this data to generate a new data set and compare the new data set to the actual data. And that looks like this. The green line there is the actual data. The gray area behind it, which is not super visible, is the amount of variability we would expect if we ran this generative model forward over and over. And what this shows is, first of all, because the sample size are so large, the predictive regions are super small, but the data fall entirely within those predictive regions, which says that this model has enough features in it to capture everything about the data that we care about. So that's good, that's check number 1. The model has enough features. Now the question is, does it have too many features? Because if it does, we're not going to be able to make good estimates. So to check that, we're going to do another parameter recovery test. And again, what this says is I'm going to use the model itself to generate a fake data set, and then feed that data set back into the model to infer the parameters, and then check to see whether the inferred or estimated parameters are consistent with what we know the answer is. Did that. Here are the results. Top left is mu, that's the mean of the distribution of efficacy. Top right is the standard deviation of the distribution of efficacy. And the bottom center is beta, which is the slope of this function that is the selection effect, the probability of taking the test. In each case, we have the posterior mean, which is the dotted line, and the actual known parameter, which is the orange line. And for each one, the orange line falls within the posterior distribution reasonably well. It looks like our estimate for mu is a little on the low side. Our estimate for beta is a little on the high side. Sigma is great. So these results are good. Maybe not perfect, but good. So I'm going to give it a successful parameter recovery test. All of this is telling me that this model is working reasonably well, but I'm not using all the data. The posterior distributions are still super wide. And if we run this from 1 year to the next, the estimates vary quite a lot in a way that's not plausible. Like the difference in mean from 1 year to the next is not going to change very much. And the selection effect is not going to go from 0 to very strong from 1 year to the next. So all of this is begging for a hierarchical model where we can take all of the data at the same time, so simultaneously estimate the parameters for all the years and all the groups. And we can impose constraints. So if we think that mu and sigma don't change very much over time, we can either impose a hard constraint and say that they don't change at all, or we can impose a soft constraint and say that they come from a distribution and we can control the width of that distribution. Same thing with the spiky patterns. We could say that they are not at all different between groups or constrain them to be not too different. However, I'm going to leave beta completely unconstrained. So just to review, mu and sigma don't change over time. The spiky patterns don't change between groups. And I'm going to get 10 different betas to tell me how big the selection effect is for each group during each year. For male test takers, here are the 5 lines for the estimated selection effect, and it's pretty strong. It's about 25% at the low end and 75% at the high end. So quite a strong selection effect. For the female test takers, it seems to be a much weaker effect. These are on the same scale. So much stronger effect for boys than girls, apparently. Standard deviation does seem to be higher for males, and this is consistent with a pattern that's seen in lots of these kinds of things where males tend to be in the tails, higher variability. Now, do you want to know what the answer is? So for the estimated means, the posterior estimated mean for the male test takers is 508. For the underlying latent distribution, and for female test takers, 502. The distribution for males is quite wide and leaves open the possibility that they overlap entirely. So the estimated means are only slightly different. 508 versus 502 is a difference of only 6 points, compared to the difference in scores, which is 30 points. So it is plausible that selection bias accounts for 24 out of 30 points in the difference between the two. So it could explain 80% of the observed gap. In the language of Mythbusters, we would say that this is plausible. I mention that because the model has to make some pretty strong assumptions. And in particular, we are taking a deviation from a Gaussian distribution as evidence of a selection effect. And the other possible explanation is sometimes the world is not Gaussian. And it may just be that the distribution of efficacy for boys is not Gaussian. We would then have to explain why it does seem to be Gaussian for girls. So hard to say exactly what's going on, but those are some of the considerations. So I would say I think this is a useful plausibility check. It says it is plausible that selection bias explains a substantial part of the observed difference. Again, if you only remember one thing, it is that sometimes you can back out selection bias by looking at distributions of data. A couple things to wrap up. I want to look at state-level data because different states take the SAT at wildly different rates. Some, it's nearly 100%, and some, it's like down in the single digits. So that variation from state to state should provide a lot of useful information. I want to say thanks to the American Institute for Boys and Men for supporting this project, for PyMC Labs for helping me out with some of the technical aspects. I successfully nerd-sniped some of my colleagues to help me out with this project. If this is your idea of fun and you would like to learn more about Bayesian statistics, I have a talk tomorrow, a tutorial for PyMC Global, where I'll introduce Bayesian decision-making with PyMC. And that is actually the first session of a workshop that we offer, and the next iteration of the workshop is starting up in January. Again, you can get these slides by going to this link, and from there you can get links to all of the things. So I will stop there. I think we have time for questions. One, all right, thank you. Thanks. We have time for one question. Make it a good one.
Selection bias, right there.
Yes.
Which of the plots showed the fingerprint? Could you just to make sure I know which one?
Going all the way back to a raw picture of the data. Here we go. So this distribution is asymmetric in a way that kind of looks like that left side of the curve has been suppressed a little bit, and this one is much closer to being symmetric. And I think that's the difference that the model is picking up on.
Thank you.
Great, that was an excellent question. Thank you, and thank you all.